Good morning, children. I hope you were able to try all the numericals of the previous exercise. I'm sure it was quite simple, not too complicated. Now we go to the B part, pulley. Okay, you've already heard a lecture of Alok Pandey in this, but once again I'm going to tell you the important things and how to study this portion, right? So first is the structure of pulley. You just read through it, and basically there are 4 types of pulleys that we're going to see. One is a fixed pulley, other one is a movable pulley, then we'll have a combination of fixed and movable pulley, okay, and then the 4th system is block and tackle system. This system is called block and tackle system. So these are the 4 types of pulleys that we are going to see basically. Now let's start with single fixed pulley. Now in this, diagrams are very important. So whenever you study this portion, along with that, please practice the diagrams. That's very, very important. Okay. Now, so if you take a fixed pulley, so the diagram will be like this. So why is it called fixed? Because the pulley is fixed to a frame. Okay, so you have a fixed frame here. This is a frame, and then so this is a pulley. Okay, so the pulley is fixed to a frame. Okay, so it can rotate about it, and then you have a rope going around. So suppose you imagine it's like the pulley used in a well. So it's a bucket of water. You're trying to draw a bucket of water, so that will be the load, and you're applying effort here in this direction. So your effort is in this direction, trying to pull, but load is in this direction. You have to apply an effort to bring it up. Okay, so this diagram is quite simple. Then next thing is derive MA and velocity ratio of a single fixed pulley. Okay, after drawing the diagram, you should be able to derive the mechanical advantage and velocity ratio. So mechanical advantage of a fixed pulley will be, now for mechanical advantage, first of all you should have marked the tension of the string. Now every part of the string has a tension T. So T will be acting on this wire in upward direction, this string in upward direction, on this also in an upward direction. So MA is load upon effort. Okay, now this load is balanced by this tension T, or this tension force of the string is only helping this load to go up. So I can write load is balanced by tension T of the string. Same way, effort here is also balanced by tension T of the string. So my MA will become T by T, that is 1. So mechanical advantage of a single fixed pulley is 1. Coming to velocity ratio. Velocity ratio is distance travelled by effort upon distance travelled by load. One thing, children, you cannot use effort arm upon load arm. That is only for pulleys. Okay, effort arm, load arm, those terms they cannot be used in pulleys. Those are only for levers, first class, second class and third class levers. You can here write only distance travelled by effort and distance travelled by load. So no effort arm, load arm in this. Remember that clearly first. Okay, now this is a known thing. If I pull this rope down by 1 meter, the load is going to be lifted by 1 meter. Or if I take generally, if distance travelled by effort is L, then distance travelled by load will also be equal to L. So L by L, that is also equal to 1. So then we usually go MA, VR and efficiency. Efficiency is MA upon velocity ratio. So 1 upon 1, that is 100%. Okay, so this is single fixed pulley. Okay, diagram, derivation for MA, VR and efficiency. So these are the three things you should. So you can put a tick mark in your diagram, then followed by this little derivation here and the conclusions. MA is 1, velocity ratio is also 1 and efficiency is 100%. Now as usual, efficiency 100% is only for ideal cases. In practical cases it will be less than 100%. So what is the reason for that? There is always some friction at the axle or in the pulley bearings. So these are the two moving parts. One is the axle, other one is the pulley bearings. So in these 2 points there will always be some friction, and because of which there will be some loss of energy. So because of that you will not have. So the question can be, what are the reasons due to which a fixed pulley cannot have 100% efficiency in practical cases? So the reason will be friction at the axle or in the pulley bearings. Then now the next question arises. There is neither gain in speed nor gain in force. You know that usually a machine is used either for gain in speed or gain in force. If it is gain in force, MA should be more than 1. If it is gain in speed, VR should be more than 1. In this case, both are equal to 1. That means there is no gain in speed, there is no gain in force, no gain in speed. Then why do we use it? Why do we call it a machine at all, if at all? Okay. So this is another question that is asked. When there is no gain either in MA or in speed, why is it called a fixed pulley? Why is it then used? Okay, the answer will be, its purpose is only to change the direction of effort to be applied, that is, to a convenient direction. The purpose of this pulley is only to change the effort in a convenient direction. Nothing else. No gain in speed, no gain in force also. So that conclusion also you have to remember. Now we go to the next type, the second type of pulley that we have, that is single movable pulley. Single movable pulley. Now in a single movable pulley, so there's a fixed frame. Let's start from here. So one end of the pulley will be fixed. Okay, one end of the pulley will be one end of the rope will be fixed. So this is the pulley and this is the rope passing through the pulley. So the load will be connected to the pulley, the axle of the pulley, and effort will be applied at the free end. Okay. Why is it called a fixed pulley? Because this pulley itself is fixed to this fixed frame. Okay. One end of the rope is fixed. Only the other end is movable, on which we apply the effort. Then where do we apply the load? The load is directly connected to the axle of your pulley. So load is connected to the axle of the pulley. So as I pull this rope up, the pulley will move. Along with the pulley, the load will also move up. Can you understand? Initially, like it will be below, and then as I keep applying force here, both the things will move up and they will come up. So this is how a single movable pulley works. Now again, let's derive MA, VR and efficiency. Now let's mark. This is the tension of the string and this is the tension T of the string. Okay, these are two parts of a string. Now load is equal to effort is equal to T. Okay, effort is balanced by 1T because only one string is involved. But when I talk about load, it is between two strings. Okay, so both the strings are playing a role in lifting this load up. Both the strings tensions will be playing a role in lifting this load up. So what will happen? load will not be just T, it will be 2T, because T plus T you will have 2T. So this makes our mechanical advantage 2. Load upon effort 2T by T, that will be 2. Same way, velocity ratio. Now if I want to lift this load by a distance, or you can take like this, if I pull this rope by a distance D, okay, I'm pulling it through a distance D, the load would have lifted through a distance D by 2. Okay, I have lifted this, I have pulled the effort through a distance D, but load would have lifted only through D by 2. Why is it so? Because again 2 ropes are involved. Okay, so D, distance D, shared by these two, so D by 2, this will rise by D by 2, this will rise by D by 2. So finally my load will also rise only by D by 2. So that leads to me to the other thing, that is distance traveled by effort is D, whereas distance traveled by load will be D by 2. So velocity ratio will be dE by dL. dL, that will be D by D by 2, it will be 2. So velocity ratio is also 2. Efficiency will be again 100%. Okay, so diagram followed by this derivation. Okay, so this diagram and followed by the derivation of MA, and then the derivation of velocity ratio. Velocity ratio along with the explanation, and then the efficiency 100%. Okay, now again the next paragraph says, for an actual single pulley, okay, the question can be, why is the efficiency of an actual movable pulley less than 100%? Why is the efficiency of an actual movable pulley less than 100%? This is ideal case. Ideally their efficiency is 100%, but actually it is less than 100%. Reason? 2 reasons. Friction in the pulley bearings or at the axle, same. Second, weight of the pulley and string. Now remember, in a movable pulley, along with this load, the pulley also will move. Okay, you can just imagine. So along with this, as you pull the string up, this will also move up. Along with that only the load will move. So the effort you apply should be able to overcome both load plus weight of the pulley. So usually they will keep the weight of the pulley as less as possible so that it doesn't take much force. Okay, so this you should remember. Weight of this pulley also has to be lifted along with the load. So that also leads to efficiency not being 100%. So weight of the pulley and string. Okay. Now we go to the next system, single movable pulley with a fixed pulley. Now the problem with this system is, okay, MA we got 2, velocity ratio we got 2, fine, but again back to the same problem, effort has to be applied in a upward direction. So to overcome this, we go to the third type, combination of fixed and movable pulley. So in combination, so first you draw a movable pulley like what you have here. And then this string that is coming out, we are not applying the effort here. So we are going to connect another fixed pulley here. And then this rope will pass through this fixed pulley and come out here, and you will apply the effort here. The effort that you were applying here is being transferred to here through, it's being made to pass through another fixed pulley. So your effort is now again back in downward direction. Okay, so this is called combination of fixed and movable pulley. Now again MA, VR and efficiency, it will be the same as that of movable pulley. Okay, so the conclusion is for combination also MA will be 2, velocity ratio will be 2 and efficiency will be 100%, because this pulley is only changing the direction of application of force. This is not going to affect its MA and VR. So its MA is 2, VR is 2, efficiency is 100%. So that's how you get it. Let's see what you have to study from the book. So a movable pulley A is used along with a fixed pulley B to change the direction of effort. And then the diagram, this diagram is very important, and this note is also very important, because it says mechanical advantage and velocity ratio shown remain same as that of movable pulley, that is MA is equal to 2 and VR is also equal to 2. Okay, now the next combination of pulleys. We are now going to see about more than 2 pulleys. Now you can strike off this is not in your syllabus, and straight come here using several pulleys in 2 blocks. That's called block and tackle system. The next system that we are going to see is called block and tackle system. Now I'm sure in the previous video itself you learned to draw the diagrams and all. So this is almost one sure question that comes in the board exam. Even this time they had a question to draw a block and tackle system with 5 pulleys, and then there was a little numerical followed by that. So diagrams are very important. Please draw and practice. It's very, very important for you to draw and practice. Even now, as I draw, I expect you to draw along with me. You can pause the video and draw along with me. Maybe you would have done it before. It can be a practice again. So draw it again. So first case, I'm going to draw for block and tackle system with 5 pulleys. Okay, with 5 pulleys, and then with 4 pulleys. Now, what you do, first you draw your fixed frame, and then you draw your upper frame, and then there will be a hook here, and then you'll draw your lower frame, and then to the lower frame you will attach a load. Please use scale and pencil. Don't do with rough hand. It might not come out clearly. Okay. So upper block and lower block. Now, if there are 5 pulleys, if there are odd number of pulleys, so one block should have 3, another block should have 2. Now always remember, the upper block will have more number of pulleys than the lower block. Why? Because lower block we should keep as light as possible, because along with the load, those pulleys also have to be lifted up, right? So we are going to have 3 pulleys at the top. So these circle also, please do it properly. So 3 pulleys at the top and 2 pulleys at the bottom. Now next is how to put the string. How to put the string. I use a technique like this. If there are odd number of pulleys, you start the winding from below. Okay, these 2 hooks should not remain attached, remember that. So you start your winding from here, go through this one, go through this one, then through this, then through this, then through this, then through this, and then comes down as effort. Now the question is, why can't we start from here? Now just try. If I start from here, it goes through this, comes here, and then goes. Again, I have to overlap it. Okay. Only if I start from here, the rope goes through every pulley and comes out in downward direction from here. Okay. Now, then they will ask you to derive its MA and VR. So mark the so if it is 5, there should be 5 T's. Okay, 1, 2, 3. This is also a string, and then there is a T here, and there is a T here, and there is a T here also. Okay, there will be 6 T's. Okay, then labeling. Labeling is very, very important. Now, what are the labelings? I'll show from the book, or you can just note it. This is called upper block. This is called upper block and this is called lower block, and the rope is called tackle. The rope is called tackle. And then below the diagram you can mark L is load, E is effort, and T is tension. Okay, these labelings are expected from you, so don't forget to do that. And please don't join these two hooks, that will be wrong. Then they'll tell you to derive MA, VR and efficiency as usual. Now, how will you start? Load is balanced by 1, 2, 3, 4, 5. 5 T's. So, L will become equal to 5T and effort will be equal to, effort is balanced by just 1T. So, E is equal to T. So, my MA will become load upon effort 5T by T, that is equal to 5. Then, coming to velocity ratio. Now, if I pull this rope down by a distance D, the load would have lifted by a distance D by 5. Because this drag of the rope has to be shared by these 5 ropes. 1, 2, 3, 4, 5. All these 5 ropes have to share this pull. Okay, that is movement of distance D. So each one has to move by a distance D by 5. So the load will also move up by a distance D by 5. So what will happen to my velocity ratio? So distance traveled by effort upon distance traveled by load. Distance traveled by effort is D and distance traveled by load is D by 5. So this will also come out to be 5. So my velocity ratio is also 5 and efficiency as usual will be 100%. Okay, so this comes as a 3-mark question. Okay, so let's look at the book. Now I expect you to pause the video and draw this block and tackle system with 5 pulleys, derive MA, VR and efficiency. Please practice it, it will be of great help. So in your book they have given one is with 5 pulleys, other one is with 4 pulleys. So labeling is important. So these are the labelings: effort, load and tension. And if it is 4, if you have even number of pulleys, upper block should have 2, lower block should have 2. So 2, 2. And the rope should start from the upper block, the upper hook. Okay, from this hook it will start. So it will go like this, like this, like this and like this. Now see what will happen if I start from the lower block. If I would have started from the lower hook, I'll go like this, like this, like this, like this and come up like this. Again my effort will be in upward direction. Then there's no point, there's no use of it as a pulley. So that is why I have to start from upper block. Here I start from the lower block, here I have to start from the upper block. And then same way you have to do the derivation of MA, VR and efficiency. Okay children, then same here, efficiency is 100% only in ideal cases. In actual practice it is less than 100%. Why? There is some friction in the bearings of the pulley, and second, weight of the string along with the weight of lower block with pulleys is not negligible. In single movable pulley at least you had only 1 pulley. Here there are 2 pulleys. You have to lift both the pulleys along with the load. Now initially this whole part will be somewhere down. Okay, now as you pull the string up along with these pulleys, the entire block will be moving up. Okay, so this weight is also has to be borne by this effort. So always they'll try to keep it as light as possible. Still you can't make it 0. So that's another reason why efficiency cannot be 100%. So these 2 points can make a note of it. Then we'll go to the last part of this chapter. Effect of weight of pulleys on MA, VR and efficiency. As I told you before, the lower block pulleys also have to be lifted along with the load. So usually they try to keep its weight as low as possible. Now how does the weight of the lower block pulleys affect its MA. Okay. So now, so I'm taking W as the weight of the lower block pulleys. Okay. W is the weight. Let W be the weight of lower block pulleys. Only lower block, not upper block. Remember that. Now, what will happen? Effort, as usual, will be balanced by T. Now, usually we write load is balanced by phi T. Okay, or let's take general, it is NT. Let's take there are n number of, let's take there are n number of pulleys. So L is equal to N into T. But practically not only L plus, but L plus W both have to be balanced by this NT. Did you get this point, children? Effort is balanced by T as usual. But so here we only wrote L is equal to phi T. But the load will not just be this load. Along with this, the weight of the lower block should be considered. So in place of load, I will have L plus W. That should be balanced by NT. Okay. So what will be load now? NT minus W. So my E is T, my L is NT minus W. So MA will be load upon effort, that is NT minus W upon T. So NT upon T, NT and T will get cancelled. This will be N minus W by T. I can write E also, right? So conclusion is MA will be less than N, means N minus something. Because you subtract something from N, so the answer will be less than N. So practically the efficiency MA will always be less than 1. Now there is one conclusion. They will always try to keep this W as low as possible. W should be small so that this value will be small and MA will not be much lesser than N. So the question that comes is for greater efficiency, pulleys in the lower block should be as light as possible and friction in the bearings mainly they ask this as a reasoning question. Give reason why for a greater efficiency pulleys in the lower block should be as light as possible. So the answer will be, first thing you should write in the case of in the case of block and tackle system, the lower block pulleys also have to move along with the effort. Okay, that is the first thing. Lower block pulleys also have to be lifted along with the effort. Then you start this little derivation and then finally you will say MA is N minus W by E, therefore it is less than N. Velocity ratio will not change, that will be N. So efficiency will also be less than 100%, 1 minus W by NE. So for greater efficiency, this W should be as small as possible. That's the conclusion of this reasoning question. Thank you, children.